Hello, Math 105 student. In this video, we'll continue reviewing from the exam number 2 review that you were given for your second exam, which is on chapters 5 and 6. This portion will be on the questions that pertain to chapter 6. Chapter 6 was on exponential functions. 6.1 was the introduction to those exponential functions, where we identified the structure of that function and what the pieces meant. We found out that in the exponential function, a times b to the t, we have an exponential function. This is the form of the exponential function. The variable is in the exponent. We learned that a was the initial value, because if t had a value of 0 and we put 0 in there, b to the 0 would be 1, and we would be left with a function value of a. So 0a, the y-intercept, is the initial value in any scenario at time 0. The function would have value a. And we learned that b was the growth factor. That's what we called the growth factor, that solid base of that exponential function. So the early questions asked you to identify if functions were or were not exponential, and then to identify those parts which make a function exponential if it was. So in letter A, we see 125 times x to the third. We don't see a variable in the exponent. In fact, it is down there in the base. This is actually a power function from chapter 4. It's in the form kx to the p, if you remember our power functions. So this is absolutely not exponential. Okay. So we wouldn't have the pieces of an exponential function, namely the initial value or the growth factor. In letter B, we do have this form of an exponential. There's a, and there's our b raised to the t. So the initial value here would be 25, and the growth factor would be 1 plus 0.025, or we could just say 1.025. In letter C, we also see the form a times b to the t. So we can identify the initial value to be 33 and the growth factor to be 5. Then we looked at graphs. Remember the rule of 4. We are going to investigate nearly every function we look at. We're going to look at it numerically, algebraically, graphically, and also verbally, those key lenses of basically the lens through which we view a lot of mathematical concepts. It particularly pertains well to looking at functions through different lenses. So we can look at different pieces. I tend to look at the initial value first. I see 8 and I see 4. And so I know that my initial value here is 8 in there and 8 there. So I know that A and C go to graphs 1 and 2. Then I go over to the growth factor, and I see that 1.75 is a little higher than 1.65, and graph 1 is growing faster, so I know then that letter A goes to graph 1. So, by deduction, C would go to number 2, but we also see it's a lower growth factor, so that is number 2. In B and D, we can see that letter B has a growth factor which is less than 1, which means every time we multiply, it's going to be decreasing the value. If we're multiplying by something less than 1, that function has got to be decreasing in its outputs. And so that would be number 4. That's my decreasing value, my decreasing function. Okay, and we see the initial value of 4 there. And so letter D has a growth factor of 1.23. It is growing slower than the others, actually, and it starts off at 4, and therefore it is graph 3. I do want you to note, too, the growth factors in letter A. That was 1.75. That means you're multiplying by 1 and 75% of something. So it's growing rather quickly, almost, it's part of the way to almost doubling each time t increases by 1. So that's a rapid growth, and that's why that is graph A. Graph C is not quite as big as 1.75, but it's a rapid growth. And then we see down here in function D, we see almost 1 1/4, so a slower growth rate happening here. So that should make sense too. Number 25. There are 2 slightly different versions here. I did alter the questions, but they're close, so I'll do both. In 25, we are to write the function given by the 2 points, and we're assuming that they are exponential. So when we're assuming that they are exponential, we know that we have that form, a times b to the t. All right, where a is the initial value and b is the growth rate. So in this case, we don't know, in letter A, we don't know what that value is, but we can actually get it. We can figure out the growth rate since t is going from 1 to 2. We can investigate what 63 over 21 is. And that is a factor of 3. So we can say that our growth factor is 3. We can actually use that nicely in this problem. It's a little bit of an easier one, to back up from that 21 and say, well, what would we multiply by 3 to get 21 at the value of 0? And the answer to that would be 7. So my initial value should be 7 times 3 to the t. Okay. In letter B, I have h of t here. To find the growth rate, again, when we're given function values for which t is only 1 unit apart, we take the ratio of the function value to the previous. So 800 over 1,000 would be the same as 8 over 10, or 0.8. We should double check. 640 is my next function value, and divide that by 800. That's the same as 64 over 80. Divide those by 8 each, and I have 8/10, and that is also 0.8. So that's a good thing. It verifies that this is in fact exponential, as the growth factor is consistent. So I have the growth factor of 0.8, and this function is nice because it gives me the initial value of 1,000, so I can put 1,000 in there. Okay, so what does h of 0 or m of 0 mean graphically? Well, 0 is the input, so that would be my 0 input, and whatever I get as an output would mean my y-intercept. So that was a question I had on my review for my students. This was the question that was on the regular review. It's very similar. The regular review just asked students to fill in the first value. It gave you the growth factor. I kind of wanted my students to figure that out, but that growth factor, again, excuse me, that initial value would be 7. So that's the missing value. In this particular problem, we see things going down. We can take the ratio for that growth factor. We take 600 over 800. We get 6/8, right? Which is 3/4. And that makes sense because b would be less than 1. We see a decreasing curve. And double checking for 50 over 600 would be 45 over 60. And that again, if we divide by 15, would give me 3/4. So that growth factor is 3/4. And here it's nice because 800 is seen there as the initial value. So 800 times 3/4 to the t. And letter A is 7 times 3 to the t. Number 26. Write an expression that represents the final value of a property that is initially worth 75,000 and increases tenfold. Well, tenfold means 10 times. So we have 75,000 times 10. Okay. 5 times, so 75,000 would increase 5 times by a factor of 1.78. So it must be multiplied, since it's growing by a factor of 1.78. Its growth factor is 1.78, being multiplied by 1.78 5 times. If you think of it that way, or literally read the problem, it would be 75,000 times 1.78 times 1.78 times 1.78. You could write it that way, but we have a shortcut in math, which is an exponent, 1.78 to the 5th. Okay. The following exponential function describes a quantity. What does it tell you about how the quantity grows? So this again, we are taking a function and interpreting what it's telling us in terms of the context of the problem. The value of a commercial property in millions of dollars after 2 years is given by this. So we would say that the initial value is $10 million. It's growing at a growth factor of 1.085, but that doesn't make sense in real language. So if you remember in section 6.2, we talked about growth rates. That 1.085 is the same as 1 plus 0.085, and that is 8.5%. 8.5%. So property starts at $10 million, grows by 8.5% each year, grows in value. That's how we would interpret that. Number 28, we're back to thinking about things graphically. Sketch a graph of 100 times 0.8 to the x. So I would notice immediately looking at this, my initial value or my y-intercept is 100. So I start at 100 on the y-axis because when x is 0, and x is 0, y is 100. I see a growth factor of 0.8 that is less than 1, which means each time I'm taking 80%. So 80% of 100, if I calculate 0.8 times 100, I get 80. That's the same as putting a value of 1 in for x. So after 1 year or 1 minute or whatever the problem would be, I have a value of 80. you can see that this is going to be a decreasing curve or an exponential decay. If I were to put 2 in, I'd be taking 80% of 80, which I think would be 64, and so on. This curve never ever crosses the x-axis, but does get infinitely close to it. So it is, the x-axis is a horizontal asymptote for that curve. Now we're practicing representation, different algebraic representation for changing functions into the exponential form of the function. So we see 22 times 3 to the 2t, and we want to write it in this standard exponential form with a base to the t. So you want something just to the t. 22 times 3 something to the t. Well, when I multiply exponents, that is by taking an exponent on the inside raised to an exponent on the outside. So 3 to the 2t is equal to 3 squared to the t. But that is the same as 9 to the t, because 3 squared is 9. So this is another way of writing q of t, 22 times 9 to the t, the initial value being 22, and the growth factor being 9. When do we subtract exponents? We subtract exponents when we have a ratio with that same base. Or we could think of 2 to the t plus negative 2. We add exponents when we have two exponential values being multiplied. So we could think of it either way. Okay? So 20 times 2 to the t minus 2, I'll think of it like this first one. 20 times 2 to the t over 2 squared. But 2 squared is simply 4. And this is interesting. I've seen a few things happening with students. That 4 is being divided by actually the whole quantity. And it doesn't matter that it's just under the 2 to the t right there. It's in the dividing position. So it doesn't matter if you put it there or if you put it there. Group all your numerical values kind of together in a lump to keep things clean, and you'll see that that initial value comes out to be 5. Okay, so that's the other way to write q of t as 5 times 2 to the t, with the initial value of 5 and a growth factor of 2. Number 30, let p of t equal 2600 times 1.03 raised to the t, and that gives a population of a town t years after 2004. What do the following expressions tell you about the town? There was a little typo on the review. I said f of 0. We so often use f as the function, so in typing that's just what was running through the person's mind. F of 0 should be p of 0. Okay, so that means 0 years after 2004, and this is a function value, so it's the function value. P is the function value, which is population. Okay, so it's really the number of people. That's what the function value is. If you think about what's happening here in the function, we have t years after 2004, and we have the population being the function of that. So this is the output, which is population, at t equals 0. So that means at 2004. We can actually see what that is. The initial population in 2004. at time t years after 2004, and we can actually see what that is. That's 2600, which we know is the initial value. So likewise, P of 3.5 would be the population of the town 3.5 years after 2004. So this is a little sketchy. I'm going to assume that we're measuring at the beginning of 2004. So 3.5 years after the beginning of 2004 would be like midway through 2007. So that's what I'm making an assumption in saying that. So this is the population of the town 3.5 years after 2004, mid 2007. And if we calculate that, that would be 2883. So slow growth of 3%. Number 31. After being treated with bleach, a population of 2,500 bacteria begins to decrease each minute by 1/2. Find a formula for f of t, the number of bacteria after t minutes. So on my version, I changed it because even if you were thinking wrongly when you did the regular number 31, you'd still get it right. So I wanted to make that clear what was going on. So the initial value of bacteria was 2,500. And we're decreasing each minute by 1/2, which means we would take what was there and decrease it by half. Okay, so the final answer is 2,500 times 1/2 to the t, which is, you'd get that even if you thought incorrectly about the problem. So I changed it on my students' version to, it decreases by each minute by 1/4 of what was there. So on my students' paper, the solution should be 2,500 times 1 minus 1/4 to the t, or you could simply write 2,500 times 3/4 to the t. Okay. But the key in this is reading. Decreases by 1/4 of what is there, right? Okay, decreases by half of what was there. All right, number 32. State the growth rate and growth factor for the following quantities. So now growth rate, if you remember, we broke off because so many times we're talking about, let's say, if you wanted to take your whole bill, pay your bill, your restaurant bill, but then if you wanted to add 20% for a tip, you would have to multiply by 1.2. Okay, so the 0.2 would be the growth rate. Okay, how much more are you paying? The growth factor is 1.2 in and of itself, but the growth rate is 0.2. So we define the growth factor to be 1 plus the growth rate. Likewise, we could solve for r by subtracting 1 from both sides and say r is equal to b minus 1. So those are expressions that you should be familiar with, the difference between the growth factor and the growth rate. We kind of separate those up from one another. So here, the size of a population grows by 0.3% each year. So they're really giving you the growth rate because it's, you take the population, which is the one part, okay? If you want the population the following year, you'd take 100% or the full population, and then you'd add 3.3% onto it. Well, 0.3%, by the way, is not just 0.3, it is 0.003, okay? So there's your growth rate, and your growth factor, the whole thing that you'd be multiplying by to get the population the next year, is 1.003. In the second one, we have the area of a lake decreasing by 9.1% each year. So in this case, we are still given a growth rate, but it's got to be a decrease by 9.1%. So the growth rate would have to be a negative since it's decreasing. And when we change 9.1% into a decimal, we get 0.091. So we take that growth rate of negative 0.091 and we add it to 1. And that gives us 0.909, which makes sense for a growth factor. If something is decreasing by 9.1%, we're really taking about 90% of it each time. Okay? So that's the way I like to think about it. Number 33. Again, we're given these functions. We're asked for the growth factor, the percentage growth, and the starting value for the following. Let's see, is there a question there? No, just stating the growth, the initial value, the growth factor B, and the percentage growth or decay rate. Okay, so the first function is 147 times 1.035 raised to the t. We can see that the a value is the 147. The b value would be 1.035, and since b is equal to 1 plus r, to solve for r, we just take 1 off of that growth factor to get the growth rate, which is 0.035, and translate it into percentage. Yeah, because they requested percentage growth or decay rate, so that we would need 3.5%. In the second one, the a value, the initial value, would be 95. The b would be 0.79, and the growth rate would be that b value minus 1, so that means it would be decaying by 0.21. So negative 0.21, since it's decay, which is negative 21%. Okay. The functions v of t and k of t describe value of different investments in year t. What do the functions tell you about the investments? What type of growth does each represent? Does it represent linear growth, quadratic growth, exponential growth, etc.? So we look at these functions and we can see that this does follow, this letter A does follow the model of exponential, a times b to the t. So the initial value of the first investment in part A is $900. The investment was initially valued at $900, but then it had a growth factor of 1.5, or a growth rate of 0.5, which is 50% each year for t years. It's exponential growth. That's a heck of a growth. If you can get something that grows like that, man, invest in it. Part B, k of t is equal to 1500 plus 150t. So this is not exponential, and it is not quadratic. It doesn't follow the model ax squared plus bx plus t, okay, or ax squared. So it is linear. We see linear constant growth, 150. That's what the definition of a line is, that has constant growth, not constant growth rate, but a constant growth. I mean, the growth rate is a percentage. So this is linear, and this investment initially started at $1,500 and then grew by $150 each year. Okay, that's linear or constant. So the amount of increase, the actual dollar amount, is at a constant growth rate. That's what linear means. Exponential, it would be a continuous growth rate, as a percentage or a proportion of what's there, whereas linear functions, there's a steady growth by a certain amount each year. 35, find the growth rate, R an annual growth factor, B for a quantity. That quadruples each year. So now we're looking at interpreting the growth factors and rates from a word description here. So the growth factor is what would be known here by the quadrupling idea. This gives us really the growth factor. So I would say the growth factor is 4, because it quadruples each year. Now, since b is equal to r plus 1, then to get the growth rate, we'd have to take 1 off of the 4. So it would really grow by 300%. Doesn't tell you how it wants r, so either 300% or 3 should be satisfactory for that problem. In the second one, it says it grows by 100% each year. So since it grows by 100% each year, that's really telling you a growth rate of 100% or 1. Okay, so you have to kind of figure out that that's telling you a growth rate instead of growth factor like the first one was. So since r is 1, 1 plus 1 would be a value of b, which is 2. Basically doubles, right? If it grows by 100%, you're doubling it. That makes sense. Always look back and see if it makes sense. Number 3, could the table give points on the graph of an exponential function y equals a times b to the x? If so, find a and b and the function a b to the x. So we look at this table and we know that at 0, it's 6. At 1, it's 7.2. At 2, it's 8.64. At 3, it's 10. These are not easy numbers to think about without a calculator. But if I think graphically too, I can see at 0, it's 6 right there. At 1, it's just, it's 1.2 more. There, maybe at 2, it's like 1.44 more, so it's a little bit more. And at 3, it's even a little bit more than that. So it looks like it has potential to be an exponential growth, but that's not definitive either. So what is definitive is if you take the ratios. Remember, if I take 10.368 and I divide by 8.64. 10.368 divided by 8.64, I get 1.2. So that ratio is 1.2. But that's not sufficient. You'd get any ratio for that. What needs to be the case is that you would have this growth rate consistent for all ratios. So you need to check all the ratios. So you have to go 8.64 divided by 7.2 as well. So this one as well. 8.64 divided by 7.2. And lo and behold, we get 1.2. So it's looking good, but it could still screw up for the last one, so you better do that. There's only 3 calculations to make, and it's easy. So 7.2 divided by 6, and that would be as well, you guessed it, 1.2. So yes, this is an exponential function, yay, because all of those ratios are the same. Okay, that proves the growth factor to be 1.2. So my growth factor is 1.2. My initial value is nicely given to me right there to be 6. So my function is 6 times 1.2 to the x. Okay? Number 37, tell whether the solution to these equations are in the following interval. Greater than 1, is x greater than 1? Is it between 0 and 1? Between -1 and 0? Or is it less than -1? Okay, so there's a whole bunch of ways you could think about this type of stuff. I would recommend, if it's possible to, you just kind of guess and check, right? If it's possible. In letter A, we have 4 to the x equals 9. Now I know that 4 to the 1 is 4. And I know that 4 to the 2 is 16. So I want 4 to the x to be equal to 9, and 9 is in between 4 and 16. So I think about my 4 to the x curve like this. I know that's increasing. I know that when I put 1 in, I get 4, and when I put 2 in, I get 16. My graph is not to scale. It doesn't matter since I'm labeling it. I know that it's got to be in between here. to give me an output value of 9. So it's in between 1 and 2. So it's greater than 1. X is greater than 1. Okay. The second one, I have 5 times 4 to the x equals 15. I want to get rid of that initial 5, so I'm going to divide both sides by 5. Divide this side by 5, and that 5 is gone. Divide that side by 5, and I have 3. So 4 to the x is equal to 3. So first of all, since 4 to the 1 was equal to 4, I know that it's got to be less than that, okay? And 4 to the 0, I know is equal to 1. Okay, so here's my curve like that. I like to think graphically. It gives me a sense of what's between what, a little bit more visually. So if I'm looking for 4 to the x to be equal to 3, I know that that's going to be like right up about there. So I know my x value has to be between 0 and 1. You know, again, you could just play with the numbers if you're not comfortable thinking graphically like I am. You could say, oh, I know 4 to the 0 is 1, and 4 to the 1 is 4. You would have to understand that this is an increasing function, and since 4 to the 0 is 1 and 4 to the 1 is 4, that 3 lies between 1 and 4, so x would have to be between 0 and 1. And then the last one down here, 1/4 raised to the x is equal to 3. So again, 1/4 to the x, that's an exponential decay curve. Again, if x is 0, I have a value of 1 always. If x is -1, if I put a -1 value in there, since I knew that it's going to be exponentially decaying, I knew that because b is less than 1, right? If I put a -1 in there, 1/4 to the -1 is equal to, reciprocate that, 4. That's up there at 4. And since I'm looking for where it's 3, I know that my x has to be now between -1 and 0. I love thinking graphically. But again, you could play around with values and you could go, well, you know, if x is equal to 1, maybe if I wrote it in a table, maybe you like tables. You know, if you like tables, that could work too. Numerically thinking about the function, all sorts of great ways. So I'd be thinking x and 1/4 to the x. And if I put in 1, I'd get 1/4. If I put in 0, I'd get 1. If I put in -1, I'd get 4. So since 3 is between 1 and 4, I know that x would have to be between 0 and -1. You can think about it that way. You know, whatever trips your trigger. Numerically, graphically, you know, both are good. Number 38. This was the original problem at the top. Given q of x is equal to that function, t of x is equal to that function, m of x equals to that function, solve q of x equals t of x, and then 3 times q of x equals to m of x. I rewrote it for my students, and because that's the first thing you do anyway, I put q of x in 3 to the 2x minus 4, and I put t of x in 9 squared. And then I did the same thing over here in part B. So the strategy here, that's what's really key when you look at these problems. What strategy are you going to use? You just look at this and go, well, it looks like I have a 3 to some junk and I have a 9 to some junk. 3 and 9 are connected because 9 can be re-expressed with a base of 3. So the strategy is to get common bases. If you can get the bases to be the same, and by bases we mean that number that's down there, not in the exponent. If you can rewrite those expressions to have common bases, then you can set the exponents equal. That's the strategy, right? Okay, that's an important strategy to know when you hit these particular problems. So I look at this thing and I go, okay, well, 3 to the 2x minus 4 is equal to 3 squared, because 9 can be written as 3 squared. So I just replace the 9 with 3 squared. But 3 squared squared is 3 to the 4th. Now notice I take care, even though it's a little bit, tedious to rewrite each line. I've found that in grading many papers over the years, not doing so leads to more errors. Students who actually understand the content screw themselves up by skipping those lines for clarity. It's sad, but true. So I would be as clear as possible and rewrite that line. Now that I have common bases, okay, I have 3 in both cases, I just take the exponents and I set them equal. 2x minus 4 equals 4. And then I solve for x by adding 4 to both sides and dividing by 2. So x is equal to 4. And of course, at the very end, you should always check that. I don't know if that's what I have here. Yeah, do I? Oh no, that's the second method. I would always check and go 3. This is my check. 3 to the 2 times 4 minus 4. What does that equal? That's 3 to the 8 minus 4. And that would be 3 to the 4th. Does that equal 9 squared? You can calculate them, or you can think about it. 3 times 3 is 9. Times 3 times 3 is another 9. So that is true. Absolutely. But you can plug it in your calculator if you like that too. I do have a second method. You could actually, because there's a 2 sitting right here in this exponent, you could have chosen to rewrite both as with a base of 9 in this particular case. So if I factored out a 2 from that first exponent, I get 3 to the 2 x minus 2, then I could say that's the same as 3 squared to the x minus 2. I'm working to get both bases to be 9 instead of 3 in this alternate solution method. So then I have 9 to the x minus 2 equals 9 squared. Then I set both exponents equal. X minus 2 equals 2. So x is equal to 4. Either way you do it, you should get the same thing. Okay? In this particular one, all bases are 3, so it's not, we don't employ that strategy, but that strategy is really important. And in knowing my course coordinator, this strategy will be employed on your exam. So in letter B, I don't see that I have to change any bases, but I do see that I'm going to have to use properties of exponents, and think about that first 3 as 3 to the 1. I kind of wrote that in there, but we should understand that if there is no exponent on there, on that 3, it is a 1. Okay? So then how do I combine these two 3's? Well, if I have two things with the same base and different exponents, I add the exponents. So that left side becomes 3 to the 1 plus 2x minus 4, and that 1 and that negative 4 combined to give me 2x minus 3. Now I have the same bases, one base on each side, same bases, and so I let the exponents be equal. 2x minus 3 equals 3x, and then I can solve, move the 2x over, subtract 2x from both sides. I get x is equal to negative 3. Then again, you can check that. I'm not going to take the time here, but you actually should, especially on a test, plug that right back into your original equation, see if it's true. You'll catch errors that way. Number 39, suppose that a sample of 108 million bacteria is needed from the population given in millions by Q equals 4 times 3 to the T after T hours. And the population is large enough for your experiment when 108 equals 4 times 3 to the T. Find the time that is needed for this event to happen. So he wants you to solve for T. So it's like solving for equations. You undo anything that you can do. So I see a 4 sitting out here, and I'm going to divide both sides by 4, my first thing. Well, 108 divided by 4 happens to be 27. 27 equals 3 to the T, which is really nice because I know 27 is equal to 3 to the third. And 3 to the third is equal to 3 to the T, so that means T must be 3. So the answer is 3 hours. Number 40, it's the same problem, except now we want 55 million bacteria. That doesn't come out as nicely because when you divide by both sides by 3, you don't get a nice number. That's power of 2. So we're thinking about this one numerically, okay? So if we put 0 into this equation, 3 times 2 to the 0 is going to give me 3 times 1, which is 3. So 3 million bacteria initially. And that makes sense because we see that's the initial value. If I put 1 in, 3 times 2 to the 1 gives me 6 million bacteria. 3 times 2 to the second will be 3 times 4, which is 12 million bacteria, still climbing, obviously exponentially. 3 times 2 to the third would be 3 times 8, which is 24 million bacteria. Still not enough. 3 times 2 to the fourth is 3 times 16, which is 48 million bacteria. Still not enough. 3 times 2 to the fifth, however, is 3 times 32, which is 96 million. So somewhere in between 4 and 5, we reach 55 million bacteria, which we want. So it's not clear, but the numerical value is going to be between 4 and 5 for T. I don't have anything better than that from this table. I could continue to test some numbers in between 4 and 5 if I wanted to get closer. Okay. You could use Desmos to graph the function y equals 3 times 2 to the t, and 55 million right here. You could graph that and find where those two graphs intersect and what t value that would be true for, and you would find that that is between 4 and 5. Number 41 says a bank account begins at 15,000 and earns 2.5% interest per year. When does the balance reach 62,000? So the first thing we want to do is write an exponential function for the balance b based on time. So the initial value again is 15,000. This is going to be our growth rate, 2.5% interest. That's our growth rate. So our growth factor is 1 plus 2.5%, which would be 1.025. So 2.5% is 0.025, and that added to 1 is 1.025 raised to the t. So there's the exponential function for balance b based on time. So we're going to solve for t to find out when this lovely function, when 15,000 invested at 2.5% reaches $62,000. It's not an easy function to solve. You could divide off 15,000 from both sides, or you could just graph both sides separately. I mean, we're going to need to graph this because we don't know how to solve those exponential functions just yet. Will in the next chapter. It's really nice. But you will need to graph this, and you will need to play with the window size until you can see what you need to. Okay? But understand that since the rate is so low at 2.5%, it's going to take a while for 15,000 to be 62,000. So you'll need a lot of years on the x-axis. So just be ready for that. Okay. Well, I graphed it and I trimmed it here. So as you can see, I put in 15,000 times 1.025 to the x, and I put in 62,000, and I had to play with the windows so I could see everything. I stretched things out until those graphs matched, and I've got a year of 57 years. So if you wanted 15,000 to be equal to 62,000, it would take 57 years under those conditions at 2.5%. All right, 57.469 years. Don't worry too much about the rounding. You could say 57.47 years. Number 42. So for x, again, we look at this and go, oh, there's a 4, there's a 64. Things look kind of fishy here. The strategy, again, you guessed it, is to get a common base. We want a common base. Okay? So I think about the 64 first as being 4 to the third. So, now I can rewrite things. I could either rewrite the 4 to the negative x, or I could rewrite the 1 over 4 to the third. I think I'll write the 1 over 4 to the third as 4 to the negative third. Just looking at that, you should be able to see that x is equal to 3. Since negative x had to equal negative 3, x is equal to 3. And then this was so easy, you should always take easy ones back and plug it in. 4 to the negative third. That would be a very easy one to figure out. That's equal to 1 over 4 to the third if you understand negative exponents, or you could just put it in your calculator and calculate the decimal for both, but it's nice to know exponents. And 4 to the third is 64. So it checks out. Always check when you can. 43. We're entering 6.5, where we did modeling using these exponential functions. Okay, and particularly here, when we're doing half-life, these would be exponential decay, because half-lives are, as they sound, each certain amount of time, you're taking half of the substance that was there, kind of like the carbon isotope, the C14 isotope that we discussed in our class. So if you begin with 2,000 grams, so begin with 2,000 grams, when will you have 1,000 grams? So that would mean that one half-life has passed to achieve half of what was there. Well, we're told that one half-life is 15 hours. So that would be 15 hours. 500 is half of that, half of 1,000. So that means another half-life must have passed. Okay, so one more half-life. So that would mean 30 hours have passed. Okay, and you're seeing the pattern now. Another half-life would have had to pass to get 250, so that would mean 45 hours in total have passed. So 500, and you can see even my stinky little graph here is not too bad in showing this pattern of exponential decay on a half-life. Now this is a different exercise right here, the hourly decay rate. So if we're given that half of this substance decays every 15 hours, but now we want to know what percentage decays every hour. So this is a more challenging kind of problem. So I'm going to start writing what I know. And when you are unsure about a problem, just start writing out some of the things you know and some of the things you're given. That's a great strategy. Well, I know that I'm dealing with an exponential function, okay? So I'm going to start with that. B of t equals a times b to the t. It doesn't have to be b of t, f of t, whatever. I just know that there's an exponential function. I also know that I'm starting off with 2,000 grams, so I'm going to put 2,000 in there. Okay. And then I know that after 15 hours, I have 1,000 grams. So that's actually a point. 15 hours, 1,000 grams. And a big strategy for when you're looking for unknowns in these problems is to use a point. Always use a point. We did that when we were doing quadratics, when we had to find the a value. We used a point we were given to solve for a. We've done this a bunch of other times, and here we're going to use a point. It could be 15, 1,000, it could be 3,500, it could be 45, 250. It doesn't matter what point you use. We're going to use a point and put it in for b, put it in for t, and for the b of t, the output, in order to solve for b. So I'm going to put 15 in for t right there, and I'm going to put 1,000 in for b of t, the output. And I'm left with an equation which only has little b in it, which is really promising. But the strategy, major strategy on these problems is to use a point, okay? Use a point. Write what you know, write the model, and then use a point. So now I divide both sides by 2,000, and I get 1/2 equals b to the 15th. And then I want to solve for b, so I am going to then raise both sides to the 1/15th. I raise both sides to the 1/15th. And I get 1/2 to the 1/15th, and please make sure you do that really carefully. I would write it to make sure that whoever's reading it on your exam can see that you know mathematically what you're doing, because then there's also the little problem of making sure you know how to enter it in your calculator, right? So I would use parentheses very carefully. So 1/2 raised to the 1/15th. And you get a b-value of 0.9548, which means every hour, like a little less than 5% decays, which makes sense. So the hourly decay rate would be, take that, if that's b, you want to find r, which you were asked for. R is b minus 1, so take b, 0.95, 48, subtract 1, you get negative 0.045 or negative 4.5%. And I can put the negative on there. Okay. Although they did ask for the hourly decay rate, so it's questionable whether you need that negative if you know that's a decay. Okay. If it's not emphasized up here that it's a decay, you would say the hourly rate is negative 4.5%. But if they say what's the decay rate, I'm not so sure you need that negative, as long as you understand it's a decay. All right. All right, number 44. A pair of points on the graph of an exponential function are given. Find a formula for the function. Round your answer for b to 4 places. All right, so again, write what you know. You know that we have an initial value of 55. If it's not there, we know that the model, the general model, is a times b to the t. Okay, so a is 55 in that model. And the second point is lower. We're going to know that we have an exponential decay. We can expect b, our exponential base, to be less than 1. Okay, and again, we see the fact we're going to use a point, that other point, to get b. We have one missing part in our exponential function. It's b. We were given a. We need to find b. We're going to use a point. This is that strategy of use a point. Okay? Use a point to get b. So we put 8 in for t and 12 in for g. And we get that. Now we're going to solve for b. First thing we want to do, or undo really, is at 55. So we divide both sides by 55. And then in order to undo the exponent of 8, we raise both sides to the 1/8. 12 over 55 raised to the 1/8 gives me a b value of 0.8267. And then we put it all together to give our final model of 55 times 0.8267 to the t. How do you check? You put the points that you were given back into that function and make sure they work. We see that the model we got is in fact an exponential decay model since b is less than 1. Now does it work? Does 8, 12 work in that model? If I put 8 in for t and calculate that, would I get something really close to 12? There's going to be a little round off error, so maybe 11.999. And obviously put in 0.55. I can actually do that visually. If I put 0 in for t, that's going to be 1 over there, and I do get 55. So I know that point works. But check the other one. If the other one works, you got the right answer. Number 45, pretty easy after 44. You're again asked for an exponential model. The formula in the form a b to the t for exponential function described. The population of people in a small town of 1,300 grows by 1.5% each year. So that's a growth rate. That's r. So b is going to be 1 plus r, and r is 0.015 as a decimal, 1.5%. So b is 1.015. A was 1,300. That's the initial value of the small town. So my exponential model is f of t equals 1,300 times 1.015 to the t. 46, an account growing at a constant percent rate contains $3,000 in 2007 and $7,000 in 2015. What's its annual growth rate? Express the account balance as a function of the number of t years since 2000. Round your answers for A and B to 4 decimal places. So if we're talking about since 2000, this point right here would be 3,000. And this point right here would be 7,000. Okay. So again, I think about what do I know? I know a b to the t is going to be my function. Oh, I guess I wrote that there. Those are always in t comma f of t. I know a b to the t is my function. And now I'm going to use both points. I'm not given the a here, sadly, since my year 0 is 2000 and I don't have the value in 2000. So I plug in my first point. And these are a little tougher because I have 2 unknowns now, a and b. So that doesn't get me anywhere. So then I put in the 3,000 point, or the 3,000 point, and I get that. Okay, now here's the special strategy for problems like this where you're not given the growth rate or the initial value. If you remember in class, we solved these by dividing these two quantities. So you basically take that upper one and that upper function and you divide it by the lower one. Okay, so you get 7,000 over 3,000 equals ab to the 15th over ab to the 7th. The a's drop out and you get b to the 8th. So this allows you to solve for just simply b, since you now have one equation in one unknown. It's really nice. So b to the 8th is equal to 7/3. Okay, so b to the 8th equals 7/3. You can solve for b by taking both sides of that and raising them to the 1/8. So b is equal to 7/3 to the 1/8. So we get the b value, and b comes out to be 1.1117. Now you go back, use another point, and that b to solve for a. So we plug in a point 3000. We don't have a, but we do have b. I would use the b that you get on your calculator, not just this truncated b. So 3000 gives me this equation, and you figure out that what 1.1117 to the 7th is, and divide 3000 by it, and you can solve for a. A is equal to 1429.5745. So now I have a, which is 1429.5785 times my b value, which is 1.117 to the t, with an annual growth rate of 0.1117. Okay. Number 47. Write a formula v of t equals a times b to the t for the exponential functions v of t as described. So v of t has that table. The first thing we're going to do is see if this is truly exponential. And again, what the growth rate is, the growth factor is, by taking all of those points and dividing them. So 45.5625 divided by 30.375, 1.5. Do it again, 30.375 divided by 20.25 is 1.5. Again, 20.25 divided by 13.5 is 1.5. So b is equal to 1.5. Okay, so we've got the b value. You could do it 2 more times, or you could divide by the b value to find when it's t equals 0, or you can use a point to solve for a. So I have v of t equals a times b to the t. I have b at 1.5, and now again, that strategy of use a point. All right, I'm going to use the easiest one, 2 comma 13.5, and I plug it in. So I get 13.5 equals a times 1.5 to the 2. 1.5 to the 2, I divide that both sides, and I get an a value of 6. So put it all together, an a value of 6, a b value of 1.5, gives me v of t equals 6 times 1.5 to the t. Now, since you go through all this work and there's so many potential for error, what I would do just to check is I would plug in 4 and see if that function gives you an output of 30.375. And you're looking good if that's the case, and then I'd maybe do the same for 5 if you've got time, and see if you get 45.565. But check, see if that function produces those values in the table. "48, you are solving some nasty looking little equations. One thing that I like to remind students of is if we have square root, just remember that that radical has really got a little 2 in there. Okay, and also I would really advise you never to take shortcuts, to write out each step super carefully, to write radicals as powers, to make sure you do the same thing on both sides and keep it legible and organized, and definitely check your answers at the end. These are really good strategies for solving equations. Just don't be lazy and skip stuff, okay? Because you'll come out on the short end without correct results. So the first thing I do in this case is write that radical to the 1/2 power. Okay. And then, because some people might incline to be doing things in an opposite order, it really clearly shows you that that 1/2 needs to be undone first. And in order to undo the 1/2 power, we would raise both sides to the 2nd power. So I get x to the 3rd plus 19. And 1/2 power to the 2nd power gives me a power of 1. So I just have x to the 3rd plus 19 equals 144. Then I subtract 19 from both sides. You can show that you're subtracting 19, or you can just do it. Let's see, 144 minus 20 is 124, but that would be 125. Okay, and then I can look at this. This is an easy one for inspection. I can say, well, what cubed is 125? I happen to know that, but if you didn't, you could raise both sides to the 1/3 power. Do that on your calculator and you will get a value of 5. And again, take that 5 and plug it back in there, right? And 5 cubed is 125, plus 19 would be 144. The square root of 144 is 12, so it does check. Really do check your answers. Don't just say you did. Actually check them. It's worth some points. So letter B, again, start by rewriting those radicals as powers. So that cube root is a power of 1/3, and that square root on the inside is power 1/2. So then we have this stuff going on, and in order to undo the 1/3 power, I would raise both sides to the 3rd. And I'm going to show it carefully. Raise it to the 3rd, 4 to the 3rd. Okay? Which you do to one side, do to the other. So the 1/3 to the 3rd becomes 1. So I'm just left with 67 minus x to the 1/2 equals 64. Okay. Now I don't like having a negative on my x, so I'm going to add x to the 1/2 to that side. 64 plus x to the 1/2. I'm going to add it to this side too and get 67. Then I'm going to subtract 64 from both sides, and I get 3 equals x to the 1/2. Now really what we're asking is what the square root of a number gives me 3, and I happen to know that's 9, but you know, walk it out if you don't see it. In order to get rid of that 1/2 power, we would raise both sides to the 2nd. And I get x is equal to 9. And this one was so complicated, and multi-step, take that back and check it just to be sure. The square root of 9 is 3. 67 minus 3 is 64. And then the cube root of 64 is 4. So that does check out. You can plug it in your calculator too if you use the powers instead of the radicals. It's kind of getting complicated. So I believe that concludes this exam review. Please don't forget before your exam to do the Wiley review, as that is worth the first 10 points on your exam. Do practice and rework questions on the worksheets. They really illustrate the types of questions and definitely the content that's going to be on your exam. Go through the examples in your notes, also your textbook, your online textbook, which is very easy and clear to read, found in your Canvas menu, sidebar menu in eText. It's a great textbook. Watch your coordinator's videos, which highlight certain skills, and those are found at the bottom of my Canvas page and your instructor's Canvas pages. And you can attend the SI reviews as well as office hours. But good luck. Hope you do well on your exam. And I hope this exam review helped. If it did, you can put a big like on the bottom of the page or send me a comment. I appreciate it. Take care. Best wishes.